The wind cut different at 8,000 feet in the northern Rockies. A former Fur Scout learned that his first winter of 1875, when frost formed inside his cabin walls and his water bucket froze 3 feet from the fireplace. He had built exactly the way every homesteader was told: heavy log walls, central wood stove, minimal ventilation, standard, and trusted. By late winter, he had burned more firewood than 3 men should need, and the cold still cut through. Across the frontier, settlers fought the same losing battle in cabins built by the book. Over the next year, this scout quietly applied an underground technique that turned -20-degree air into +50-degree air before it reached his living space. While neighbors' cabins kept burning cord after cord, his approach held steady warmth with half the wood. This video breaks down the exact steps behind his system. What did he understand about the earth that every builder should know? The ridge stretched 20 miles without shelter, catching every gust that swept down from the Continental Divide. Most homesteaders avoided such exposed ground, but the former Fur Scout had chosen this spot for reasons that made sense in autumn. Clear sight lines for hunting, timber within walking distance, and a creek that ran year-round in the draw below. What he had not counted on was how the elevation and exposure would turn standard cabin building wisdom into a death trap. By December of 1874, the pattern became clear across every cabin on the ridge. Thomas Milner, a homesteader 2 miles west, woke each morning to ice-coating his coffee pot despite keeping his fire banked through the night. His wife wrapped their infant in every blanket they owned, yet the child's breath still formed clouds in what should have been the warmest corner of their cabin. The Hendricks family, newcomers from Ohio, who had followed construction advice from a homesteading manual, discovered that their carefully chinked log walls did nothing to prevent condensation from freezing on interior surfaces. Sarah Hendricks scraped frost from the inside of her windows every dawn, watching the ice refreeze within hours. The accepted method seemed logical enough on paper. Every settler guide and experienced neighbor recommended the same approach: build with logs cut from local pine, chink the gaps with mud and moss, install a central fireplace or iron stove, and add one small vent near the ceiling to release smoke. The reasoning was sound. Wood was abundant in the surrounding forest. Fire had warmed humans for thousands of years. A single opening would let smoke escape without wasting heat. Most importantly, the system required no special materials or complex construction that frontier families could not manage with basic tools. Yet the reality of high-altitude winter exposed every flaw in this conventional wisdom. When January temperatures plunged to -25 degrees Fahrenheit, the COO, central heating principle, collapsed entirely. Fires that burned hot enough to warm the area directly around the stove created brutal temperature gradients throughout the rest of the cabin. Floors stayed cold enough to numb feet through thick boots. Walls became condensation traps that froze solid each night, creating ice buildup that cracked chinking and rotted logs. The single ceiling vent, meant to release smoke efficiently, became a chimney that sucked heated air from the cabin while pulling frigid replacement air through every gap in the walls. The fuel consumption alone threatened survival. Families that had calculated 1 cord of wood per month found themselves burning nearly a cord each week just to maintain temperatures above freezing. Men spent entire days cutting and hauling timber, leaving little time for other essential winter tasks like hunting, tool repair, or maintaining their cabins against the constant freeze-thaw cycles that loosened logs and opened new gaps. Some neighbors began burning furniture and floorboards to stretch their wood supply, weakening their shelters in a desperate attempt to stay warm. The scout watched this pattern repeat across the ridge with growing frustration. Unlike his neighbors, he carried memories that did not fit the standard frontier narrative. His grandmother had described the stone cottages of her childhood in northern Germany, where thick walls stayed warm through brutal winters without consuming forests of firewood. She spoke of root cellars that never froze, even when snow covered the ground for months. More recently, during his trapping years, he had sheltered in native earth lodges that felt impossibly comfortable despite their simple construction. These experiences had planted questions about whether standard log cabin design was truly the best solution for mountain winters. When his neighbors began to mock his inquiries about underground building techniques, the scout realized he would have to prove his theories alone. Miller called him a fool for trying to live like a prairie dog. The local supply agent who sold iron stoves and stovepipe to homesteaders dismissed talk of earth-based heating as Indian nonsense that will get you killed. Even experienced builders warned that any attempt to draw air from underground sources would fill his cabin with deadly gases or suffocating dampness. But the scout had learned to distrust conventional wisdom during his trapping years. The standard advice for avoiding frostbite, for reading weather signs, for finding water in dry country had failed him enough times that he had developed his own methods through careful observation and experimentation. He applied the same skeptical approach to cabin heating. If every family on the ridge was burning themselves into poverty while still shivering through the night, perhaps the accepted method was simply wrong. The breakthrough came from combining two separate memories. His grandmother had described how German farmers built root cellars that stayed above freezing all winter without any heating source. The earth itself, she claimed, held warmth that could be captured and used. During his trapping years, he had noticed that native dwellings often incorporated bermed earth walls that seemed to moderate temperature swings. What if these two principles could be combined and adapted for a mountain cabin? The idea that would eventually revolutionize winter survival on the frontier began with a simple question. Instead of fighting the Earth's natural temperature, what if he could harness it? While his neighbors continued to burn cord after cord of precious timber, the scout began to plan a system that would turn the ground beneath his feet into a heating source more reliable than any fire. The scout began his experiment in late February of 1875 with a calculation that would either prove his theory or bury his reputation on the ridge. At 8 feet below the surface, the Earth maintained a temperature near 45 degrees Fahrenheit, even when surface air dropped to -30. If he could route incoming air through a buried conduit long enough to absorb that ground heat, he might solve the fundamental problem that plagued every cabin, the constant influx of frigid outside air that overwhelmed even the hottest fires. His first challenge was acquiring suitable pipe. The nearest railroad depot lay 60 miles south, but a conversation with Jake Morrison, who had worked abandoned mining claims in the area, revealed a cache of iron pipes left behind by hydraulic mining operations. These sections, originally used to channel water for gold extraction, measured 4 inches in diameter and came in 8-foot lengths. Morrison agreed to trade 12 sections for a winter's supply of deer jerky, giving the scout 96 feet of conduit to test his theory. The excavation began at a point 30 yards upwind from his cabin, chosen to avoid contamination from his woodpile and outhouse. Using a pick and shovel, he dug a trench that sloped gradually downward, maintaining a consistent 8-foot depth throughout its length. The work proved brutal in frozen ground, requiring him to build fires along the trench route to soften the earth enough for digging. Each day of excavation yielded only 10 to 12 feet of progress, and the constant threat of cave-ins forced him to shore up the walls with salvaged lumber as he advanced. The pipe installation required precise attention to grade and seal. Too steep an angle would create condensation problems as warmed air cooled rapidly. Too shallow would fail to capture sufficient ground contact for meaningful heat exchange. He settled on a slope of 1 inch per 8 feet of length, creating just enough gradient to prevent moisture accumulation while maximizing the pipe's exposure to stable earth temperature. Each joint between sections was sealed with a mixture of pine pitch and clay, then wrapped with strips of canvas to prevent air leaks that would compromise the system's efficiency. The intake end, positioned well away from his cabin's wind shadow, featured a simple but critical innovation. Rather than leaving the pipe opening exposed to collect snow and debris, he constructed a wooden box that extended 18 inches above ground level. The box contained a series of horizontal slats that allowed air to enter while deflecting precipitation and blocking larger debris. A hinged lid permitted cleaning access during severe weather events. The delivery end presented more complex engineering challenges. The pipe terminated in his cabin's crawl space, where it connected to a vertical riser that brought the warmed air to floor level. This transition point required careful insulation to prevent heat loss during the final few feet of travel. He wrapped the vertical section with layers of wool cloth and secured it inside a wooden housing that directed the incoming air toward the center of his living space. Testing began during a cold snap in early March, when surface temperatures held steady at -22 degrees Fahrenheit for 5 consecutive nights. The scout used a simple but effective method to monitor the system's performance. He suspended a mercury thermometer just inside the buried pipe's entrance and another at the point where air entered his cabin. The temperature difference revealed the Earth tube's heating capacity with startling precision. On the first night, outside air entered the system at minus 22 degrees, but emerged into his cabin at 48 degrees Fahrenheit. The 70-degree temperature gain occurred without any external energy input beyond the Earth's natural thermal mass. More importantly, this warmed intake air eliminated the brutal drafts that had plagued his cabin throughout the winter. Instead of frigid currents that shocked occupants and overwhelmed his heating system, gentle flows of moderate air entered at floor level and mixed naturally with the cabin's interior atmosphere. The system's impact on fuel consumption proved equally dramatic. During the 5-day test period, the Scout burned 1 1/2 cords of wood compared to the 2 1/4 cords he had consumed during a similar cold spell in January. The 33% reduction in fuel use occurred while maintaining superior comfort levels throughout his cabin. Floor temperatures, previously the coldest area in any mountain cabin, stabilized at 38 degrees Fahrenheit. Wall surfaces remained dry and free of the condensation that had plagued conventional construction. Perhaps most significantly, the quality of indoor air improved beyond anything the Scout had experienced in frontier housing. Traditional cabins created a constant struggle between fresh air and warmth. Opening vents to improve air quality meant accepting brutal temperature drops. Sealing tightly to conserve heat resulted in stale, unhealthy atmospheres. The Earth tube solved this dilemma by providing continuous fresh air without thermal penalty. The Scout could breathe comfortably while maintaining consistent warmth throughout his living space. The success attracted attention from unexpected sources. Baptiste Moreau, a Métis trapper who had observed Earth Lodge construction during his travels on the Great Plains, visited the cabin during the test period and immediately recognized the principle. The underground lodges he had seen used similar earth coupling techniques, though they typically incorporated the living space itself into direct ground contact rather than routing air through separate conduits. His validation provided cultural confirmation that the Scout's innovation built upon proven traditional knowledge rather than untested speculation. Word of the experiment's success reached Thomas Milner by early April. Milner's own cabin had consumed nearly 5 cords of wood during the brutal March cold snap, leaving him dangerously short of fuel with weeks of winter still ahead. His initial skepticism gave way to grudging interest when he observed that the Scout's cabin maintained comfortable temperatures with fires that barely glowed compared to the roaring blazes required for conventional heating. The demonstration that underground air conditioning could work reliably in extreme mountain conditions would soon spread beyond the ridge, though most settlers remained convinced that such methods demanded too much labor and carried unacceptable risks. The Earth tube had proven its fundamental concept, but the Scout recognized that his heating revolution required additional components to create a truly superior winter survival system. The Earth tube had solved the air intake problem, but by late March the Scout recognized a fundamental flaw in his approach. Even with pre-warmed air flowing steadily through his cabin, heat continued to hemorrhage through the log walls, roof, and floor at rates that demanded constant firing of his stove. The thermal envelope itself had become the limiting factor. Traditional log construction, no matter how carefully chinked, created a barrier only 6 to 8 inches thick against temperature differentials that often exceeded 70 degrees. The Scout needed a wall system that could store heat during the day and release it slowly through the night. His solution drew inspiration from conversations with Heinrich Müller, an immigrant neighbor whose family had operated a dairy farm in Bavaria before coming to America. Müller described the construction of traditional German cattle barns, where thick walls filled with packed earth kept livestock comfortable through brutal alpine winters. These structures used a double wall technique, an outer shell of stone or heavy timber, an inner lining of planks, and a cavity between them filled with soil, straw, and clay mixed to create thermal mass that absorbed heat slowly and released it even more slowly. The Scout began retrofitting his existing cabin in early April when warming weather made construction feasible. He started with the north wall, which faced the prevailing winter winds and showed the greatest heat loss. Working from inside, He constructed a second wall of split pine planks positioned 6 inches inward from the existing log surface. This created a cavity that he filled with a carefully prepared mixture of local clay soil, chopped grass, and small stones. The proportion mattered critically. Too much clay created a mixture that cracked when it dried. Too little failed to bind the material into a solid mass. After extensive testing with small batches, he settled on a formula of 3 parts clay-rich soil, 1 part chopped prairie grass, and 1 part gravel-sized stones. This mixture, when dampened and packed firmly into the wall cavity, dried to form a dense thermal mass that conducted heat slowly and stored it efficiently. The installation process required patience and precision. The Scout filled the cavity in horizontal layers, each about 8 inches thick, using a wooden tamper to compress the material and eliminate air pockets that would reduce insulation value. The roof presented even greater challenges. Standard log cabin construction used simple board planks covered with split shingles, creating minimal insulation against heat loss through the cabin's highest point. The Scout solution involved layering the roof with materials that would trap warm air and create thermal mass above the living space. He began by installing a vapor barrier of pine pitch and canvas over the existing roof boards, then added 6 inches of mixed soil, grass, and clay identical to his wall formula. The structural demands of this earth roof required reinforcement of his existing framework. The added weight of wet soil threatened to collapse roof supports designed only for snow loads and wood shingles. He installed additional support posts in his cabin's interior and added diagonal bracing between existing rafters. The investment in structural upgrades proved essential when spring rain saturated the roof soil, creating loads that would have crushed conventional cabin construction. Waterproofing became the most critical aspect of roof construction. The Scout learned this through painful trial and error when his first attempt allowed moisture to penetrate the earth layer and drip into his living space. His solution involved multiple redundant barriers. Over the original roof boards, he applied a thick coat of pine pitch mixed with charcoal dust. Above this, he installed a layer of birch bark sheets with overlapped seams sealed with more pitch. Only then did he add the soil mixture, sloped carefully to drain water toward gutters he had fashioned from split logs. The floor system required the most innovative approach. Traditional cabin floors consisted of split logs or rough planks laid over bare ground, creating a massive thermal leak that drew heat downward into the earth. The Scout's thermal mass floor inverted this relationship, using the ground as a heat storage medium rather than a heat sink. He excavated 18 inches of soil from his cabin's interior and installed a foundation of flat stones laid in sand. Over this base, he constructed a floor of clay, sand, and chopped straw mixed to the consistency of thick mortar. This adobe-style floor served multiple functions beyond insulation. During the day, heat from his stove warmed the thermal mass, which stored that energy and released it gradually through the night. The dense material eliminated the drafts that plagued raised wooden floors. Most importantly, the thermal mass helped moderate temperature swings, preventing the extreme variations between scorching heat near the stove and bitter cold in distant corners that characterized conventional cabin heating. Testing of the complete thermal envelope system began during a late April cold snap that brought 3 nights of temperatures near 0 degrees Fahrenheit. The results exceeded even the Scout's optimistic projections. His cabin maintained interior temperatures above 50 degrees, with fires that consumed less than half a cord of wood over the 3-day period. The thermal mass walls absorbed heat during active burning periods and continued radiating warmth for hours after the fire had died to coals. More significantly, temperature distribution throughout the cabin became remarkably uniform. The thermal mass floor eliminated cold spots near exterior walls. The earth-filled walls prevented the formation of frigid zones that had previously made large portions of his cabin unusable during severe weather. For the first time since arriving on the ridge, the Scout could walk barefoot on his floor throughout the night without numbness or discomfort. The system's performance during the transition to summer weather revealed an unexpected benefit. The thermal mass that had stored heat during winter now absorbed excess warmth during hot days and released it during cool nights. His cabin remained comfortable while neighbors sweltered in structures that trapped daytime heat and radiated it back to occupants throughout the night. The same thermal envelope that had solved winter heating problems proved equally valuable for summer cooling. Thomas Milner, who had observed the earth tube experiments with skepticism, could no longer dismiss the Scouts' methods when he visited during the April testing period. The comfortable temperature, clean air, and obvious fuel savings provided undeniable evidence that Earth-based construction could outperform traditional techniques. Yet Milner remained reluctant to commit the labor and materials required for such extensive modifications to his own cabin, preferring to endure known problems rather than risk unknown complications from untested methods. The thermal envelope had proven its effectiveness, but the Scout recognized that moisture. Management would determine whether his innovations could survive the coming spring thaw and summer storms. The Scout's first spring with his modified cabin revealed a problem that threatened to destroy everything he had accomplished. As snow began melting in early May of 1875, water penetrated the earth-filled walls and pooled beneath his thermal mass floor, turning his carefully crafted insulation into sodden clay that lost its heating properties and began to smell of rot. Moisture trapped inside his sealed cabin created condensation that dripped from the ceiling and formed puddles that never dried. The very thermal mass that had saved him through winter now threatened to become a breeding ground for mold and structural decay. The crisis forced him to understand ventilation as more than simple air exchange. His earth tube brought fresh air into the cabin, but provided no mechanism for removing the moisture-laden air that accumulated from cooking, breathing, and the natural humidity released by drying clothes and melting snow tracked indoors. Traditional cabins relied on their numerous gaps and poorly fitted doors to provide this exhaust function, but his sealed thermal envelope trapped humid air with dangerous efficiency. His solution came from observing the design of Native American earth lodges during a trading visit to a Mandan settlement along the Missouri River. These structures featured central smoke holes that served dual purposes, releasing smoke from cooking fires and creating natural updrafts that pulled stale air from the living space. The key insight was that warm, moisture-laden air naturally rose and could be captured and expelled without mechanical assistance if provided with the right pathway. The Scout designed his exhaust system around a vertical stack that extended from his cabin's interior through the roof and 18 inches above the highest point. He constructed this chimney using salvaged stovepipe sections sealed with the same pine pitch and clay mixture he had perfected for other joints. The critical innovation was the stack's interior diameter of 6 inches, significantly larger than typical stovepipes, allowing it to move substantial volumes of air without creating back pressure that would interfere with his heating system. The bottom of the exhaust stack connected to a collection chamber positioned at ceiling level in the cabin's center. This wooden box, measuring 2 feet square and 8 inches deep, gathered warm air that naturally accumulated in the cabin's highest space. Slots cut into the chamber's sides allowed air to enter from all directions, while a single opening at the bottom connected to the vertical stack. The design created a gentle but constant updraft that pulled moisture and stale air from throughout the cabin without creating the harsh drafts that would compromise heating efficiency. Testing the passive exhaust system required careful attention to balance. Too much airflow, too much, would waste the heat generated by his thermal mass system. Too little would fail to control humidity and air quality. The Scout experimented with dampers made from thin wooden plates that could partially block the stack opening during extreme cold, then open fully during milder weather, when moisture control became more important than heat conservation. The results proved immediately obvious. Within days of installing the exhaust stack, condensation on his windows disappeared. The musty odors that had begun developing in his earth-filled walls faded as dry air circulated through the thermal mass materials. Most importantly, the humidity levels dropped to comfortable ranges that prevented the mold growth that had begun threatening his insulation system. But spring runoff presented an even more serious challenge to his earth-based construction. As 3 feet of accumulated snow melted rapidly during unseasonably warm weather in late May, water flowed directly against his cabin's foundation and seeped into the thermal mass walls from ground level. The earth fill that had performed so well in dry winter conditions became waterlogged and began slumping away from the inner wall planks, creating gaps that eliminated insulation value and threatened structural integrity. The scout's response involved elevating his entire cabin above the flood zone using techniques borrowed from Heinrich Müller's description of European farm buildings constructed in wet climates. Working frantically as spring runoff continued, he excavated around his cabin's perimeter and installed a foundation skirt of flat stones laid in mortar made from local clay and sand. This raised base lifted his cabin floor 8 inches above the surrounding grade, preventing direct contact between ground moisture and his thermal mass construction. The stone foundation served multiple functions beyond simple elevation. Its mass provided additional thermal storage that enhanced his floor heating system. The mortar joints, when properly sealed, created a moisture barrier that prevented capillary action from drawing groundwater up into his earth-filled walls. Most critically, the raised foundation created an airspace beneath his cabin that allowed moisture to evaporate naturally, rather than accumulating in his structural materials. Completing the water management system required addressing runoff from his earth roof, which had become saturated during the spring melt and threatened to dump thousands of gallons directly around his foundation. The scout constructed a gutter system using split logs shaped into half-round channels and sealed with pine pitch. These gutters connected to downspouts made from sections of his remaining iron pipe, directing roof runoff away from the cabin to collection points 30 feet distant. The downspout installation presented unique challenges because his earth roof could not support the weight of traditional gutter hangers. Instead, he built wooden brackets that distributed the load across multiple roof rafters, preventing concentrated stress that might damage his waterproofing layers. The brackets also allowed seasonal adjustment of the gutters to maintain proper slope as the earth roof settled and shifted with moisture changes. To complete his drainage system, the scout dug shallow trenches around his cabin that intercepted surface water and directed it toward natural drainage channels in the surrounding landscape. These trenches, lined with stones to prevent erosion, created a defensive perimeter that kept spring runoff from pooling against his foundation or infiltrating his thermal mass walls. The combined ventilation and drainage systems proved their worth during the severe spring flooding of 1876, when rapid snowmelt and heavy rains created conditions that destroyed several conventional cabins on the ridge. Thomas Milner's cabin suffered foundation rot that required complete reconstruction of his floor system. Sarah Hendricks discovered that moisture had penetrated her log walls so thoroughly that several courses had to be replaced before winter returned. The scout's cabin, by contrast, remained dry and structurally sound throughout the flood period. His passive exhaust system maintained comfortable humidity levels despite the saturated conditions outside. His raised foundation and drainage network prevented water infiltration that had plagued his neighbors. Most importantly, his thermal mass walls retained their insulation properties because the water management system kept them dry even during the worst spring conditions the mountain region had experienced in over a decade. The success of his integrated moisture control system established the final component needed for year-round comfort and structural longevity in extreme mountain conditions. The winter of 1876 arrived with a ferocity that tested every survival strategy on the northern Rocky Mountain frontier. By early December, temperatures had plunged to minus 40 degrees Fahrenheit and remained there for weeks, accompanied by blizzards that dumped snow in drifts, reaching the eaves of most cabins. The sustained cold created conditions that pushed conventional heating methods beyond their breaking point and provided the ultimate proving ground for the Scouts' integrated earth-based system. Thomas Milner's experience illustrated the catastrophic failure of traditional frontier construction under extreme conditions. His cabin, rebuilt after the previous spring's flood damage, consumed 4 cords of wood during the first 3 weeks of December alone. Despite maintaining fires that glowed white-hot throughout the night, interior temperatures dropped below freezing in the corners farthest from his stove. Ice formed on the interior walls each morning, creating sheets of frost that never fully melted even during the warmest part of each day. By Christmas, Milner had burned through his entire winter wood supply and began dismantling interior furniture to keep his fire alive. The Hendricks family faced even worse conditions in their conventionally built cabin. Sarah Hendricks discovered that water froze in their cooking pots despite placing them within 3 feet of their fireplace. Their infant son developed a persistent cough from breathing air that remained damp and cold even with continuous heating. When a chinked section of their north wall failed during a particularly brutal storm, allowing snow to blow directly into their living space, they were forced to abandon their cabin temporarily and seek shelter with neighbors. The Scout system, by contrast, maintained remarkable stability throughout the prolonged freeze. His earth tube continued delivering air at 40 to 45 degrees Fahrenheit, even when outside temperatures reached their lowest points. The thermal mass walls absorbed heat during the brief periods when his fire burned actively and released that stored energy steadily for 12 to 14 hours afterward. Most significantly, his adobe floor remained warm enough to walk on barefoot throughout the night, creating a zone of comfort that extended throughout his entire living space. Fuel consumption data from the 1876 winter revealed the dramatic efficiency advantages of earth-coupled construction. While Milner burned 4 cords in 3 weeks, the Scout used 2 and 1/4 cords for the same period while maintaining superior interior conditions. His passive exhaust system eliminated the moisture problems that plagued sealed conventional cabins, preventing the condensation issues that forced neighbors to choose between warmth and breathable air. The combination of systems created a self-regulating environment that required minimal active management even during the worst weather conditions. The performance gap became impossible for neighbors to ignore when the Scout began sharing precise measurements of his system's effectiveness. Using a mercury thermometer obtained from a traveling merchant, he documented interior temperatures at multiple locations and times throughout each day. His records showed consistent readings between 52 and 58 degrees Fahrenheit in all areas of his cabin, compared to the 20 to 30 degree variations that characterized conventional heated spaces. The data provided objective proof that earth-based construction could outperform traditional methods by measurable margins. Baptiste Moreau, the Métis trapper who had initially validated the Earth Lodge principles behind the Scout's innovations, became the first neighbor to adopt modified versions of the techniques. During a February thaw that provided brief construction weather, Moreau installed a simplified earth tube system in his own cabin, using techniques adapted for retrofit installation. His version used shorter pipe sections and shallower burial depth, but still achieved a 15 to 20 degrees warming of incoming air that reduced his fuel consumption by approximately 25%. Heinrich Müller represented a more systematic adoption of the complete system. Convinced by the Scout's winter performance data, Müller began planning a new cabin that would incorporate earth-filled walls, thermal mass flooring, and integrated ventilation from the initial construction phase. His German farming background provided familiarity with earth-based construction that made the techniques seem practical rather than experimental. Müller's methodical approach included detailed material calculations and construction scheduling that demonstrated how earth-coupled building could be systematized for broader adoption. The social dynamics of acceptance proved more complex than simple technical validation. While neighbors could not dispute the Scout's superior comfort and fuel efficiency, many remained reluctant to commit the labor and materials required for earth-based construction. The installation process demanded more initial work than conventional cabin building, requiring excavation, material mixing, and construction techniques that departed significantly from familiar frontier methods. Some settlers expressed concern that earth-filled walls might attract rodents or create hidden spaces where structural problems could develop undetected. Local supply merchants initially resisted the innovations because earth-based construction reduced demand for manufactured heating equipment and fuel. Iron stove dealers warned customers that underground air systems would create dangerous conditions, despite having no evidence to support such claims. Sawmill operators who profited from high wood consumption during severe winters had economic incentives to discourage techniques that dramatically reduced fuel usage. The resistance from established commercial interests slowed adoption even among settlers who recognized the technical advantages. However, practical results eventually overcame commercial opposition and social conservatism. During the spring of 1877, structural surveys of cabins that had survived the brutal winter revealed striking differences in long-term durability. Conventional cabins showed extensive frost damage to foundation logs, crack chinking, and moisture-related rot that required substantial repair work. The Scout's earth-coupled cabin, by contrast, emerged from winter in excellent condition with no structural damage and minimal maintenance requirements. The documentation of these outcomes created a knowledge base that enabled systematic replication of the techniques. Muller's German engineering background proved valuable in creating standardized procedures for earth-fill mixing, thermal mass installation, and ventilation system design. His detailed notes included material ratios, construction sequences, and quality control methods that allowed other builders to achieve consistent results without extensive experimentation. By 1878, 3 additional cabins in the region incorporated variations of the earth-based heating system. Each installation included modifications suited to local conditions and builder preferences, but all achieved significant improvements in fuel efficiency and interior comfort compared to conventional construction. The techniques began spreading through informal networks of frontier builders who recognized practical advantages worth the additional construction complexity. The long-term legacy of the Scout's innovations extended far beyond immediate fuel savings or comfort improvements. His integration of traditional knowledge from multiple cultural sources demonstrated how frontier survival could benefit from systematic application of proven principles rather than blind adherence to conventional wisdom. The earth-coupled heating techniques he developed would eventually influence sustainable building practices that remained relevant more than a century later, proving that solutions to environmental challenges often lay in combining ancient wisdom with innovative application rather than pursuing entirely new technological approaches.